and preserving our investment, which is a gigantic investment in roadways. So where does asphalt rubber or rubberized asphalt fit into this? And you've already heard some wonderful presentations before me. I think Camille was a fabulous presentation on this, and George, I think he does need psychiatric care, but we won't get into that at this point in time. But we will talk about that later tonight when we've had a few more drinks, for that matter, and we'll discuss that. But the thing about rubber and asphalt is it's turned out to be many things. I'm going to talk about these in general to kind of build a case for why it is such an undisputably great product. As George said, when it first was developed, it was patented, and it was a very expensive product. All the patents are gone today, and it's reasonably inexpensive. It develops roadways that are safe. Of course, we want safe roads. We want all service. We want to make sure we're not driving through mud puddles or potholes. Durable, something that lasts for a long time. Economical, which is sort of like cost-effective, and environmentally friendly. Environmentally friendly is kind of a new thing. That's new in the sense that the man who invented it, going back years before, really didn't have that in mind at the time. A tire is by itself a great thing. You know, we've seen many presentations here, and we saw in a presentation where there's something about the future, what kind of highways are in the future and everything. And as I envision the future, it seems to me like there still will be tires. Now, I may be wrong, but for quite a ways in the future, people are still going to be driving on tires. So whether we're going to be driving a solar car or one that runs on batteries or whatever, it's still going to have rubber tires probably. And there's going to be trucks with rubber tires. There's going to be airplanes with rubber tires. So there's still going to be used tires. They'll need to be recycled. We'll have to do something with them. That won't change. So what about the recycled tire rubber itself? Well, it can do many things, and I've listed quite a few of them here, kind of some of the good things. And you've heard about these before. I'm not going to read each one of these, but you'll see some examples. So traditionally, asphalt rubber started out to be roughly about 80% asphalt binder or bitumen and 20% recycled tire rubber. The first version of this, actually, they didn't really use crumb rubber, interestingly enough. They used rubber buffings off of a tire. But it was back in the days when they recapped tires, and they actually peeled the rubber off of there, and so they wound up with these like shards almost. They were kind of long. And that's what they used in the beginning. So it was a little more difficult. Later on, they went to crumb rubber, and that's pretty much what everybody uses today. Different ways of expressing it, whether it's by total weight or by weight of the binder. So you have to keep that in mind for the percentage, but it's up around 20% recycled tire rubber. Over the years, that's changed. There's a lot of other products around today, besides the 15% or more, which is kind of the traditional asphalt rubber. You have amounts that are less than 15%, maybe 10, maybe 11, which work fairly well. A little smaller grind of rubber. You have it mixed with polymer, some small amount of polymer, like an SBS, which is kind of a hybrid. You have a terminal blend, which is they reduce the rubber really to, it's kind of digested, and then they add polymer to it. And then you have activated rubber, which George spoke about, and that's what we're going to see a demonstration of this afternoon, right, George? That's going to be that. So you'll explain that in more detail at that time. So lots of different forms of the application of it. Just a few general remarks about integrating it into specifications. And we heard that from our earlier speaker. That's he thinks one of the drawbacks. And that is somewhat of a drawback. If you consider the fact that the AASHTO road test, which traditionally in the United States was the Bible for designing highways, didn't really have polymer or rubber. It just had neat asphalt. So how does that fit in there? Well, okay, it didn't. It wasn't at the road test. What about the empirical mechanistic design, which I was on that panel, Camille actually was working on the research component at Arizona State University with Dr. Matt Witzak. It doesn't really have a place in there for asphalt rubber per se. It's Arizona State's done some more work with that, and there's some ways they could maneuver it in there, but it was not part of that model, if you will. So integrating it into the testing mode or even the specification mode does present some problems because historically it wasn't in there when they developed those models or those specifications for that matter. I like this quote, and the reason I like it is it's not with regard to pavements. This man is a structural engineer. He's been in it for a long time. And what he's pointing out here is even with all the wonderful software they have for designing buildings and bridges and things that we take for granted, for that matter, is going to be structurally sound and earthquake proof and not going to fall over in a windstorm or whatever, he made the point here that even with all of those models and all of that testing that went in there, there's always some room, however, for engineering judgment, that we should not forget this, that let's not just put all of our faith in the model itself. And I know our next speaker is going to be talking a lot about modeling, and he will probably have many things to say about how I'm wrong about that, but that's okay. I've only been an engineer for almost 50 years and seen some interesting things happen in that time that there were no models to fit them in. There weren't even any models, but we did them anyway. So that's what I'm trying to point out here is this convergence of wanting to try to force something into a model that really needs its own model, needs its own place, maybe its own set of special tests or whatever. Safety aspects, we don't want to build anything that's dangerous, of course. We want good skid resistance, want it to resist rutting and potholing. We want it to have a good ride, although it's not necessarily always a safety issue. We would prefer it not to be cracked. Cracked roadway by itself is not necessarily an unsafe roadway. However, when the maintenance crew goes out there to fill the cracks and they put out a bunch of signs that say move over in the other lane or whatever, that could potentially be a hazardous zone. I mean, all construction zones could be a hazardous zone. So the less maintenance, upkeep we have to do the road due to cracking, rutting, potholing, skid resistance, whatever, the better for all of us. We all will be safer because we don't want to be interrupted and at the last second have to make a decision to move over in another lane or whatever, or slow down, or stop texting on our phones, you know. People do text while they're driving. Right over there. He loves to text while he's driving. He's not the only one, though. Friction, Camille already pointed this out. We've investigated this for a long time. Open graded with rubber. Had great results. Now people will say, I've been in meetings, people say, but we can build open graded. We don't need the rubber. True. California invented the open graded friction course. It was called a plant mix seal coat, because basically all they did was take chips from a seal coat operation, run it through a hot plant and coat it with asphalt and pave it with a paver, so now you had some leveling control. And that was great. The only problem was it didn't last very long because it has about 20% air voids or more, and it has a film thickness of asphalt that's very thin, so it would not be very durable. So yes, you can do it. You can build it. Many states did that. Federal Highway Administration promoted it in the 70s. Practically every state gave up on it because with snow and ice, it just deteriorated so rapidly that it would not stand up, and under traffic. So Arizona used open grader for a long time. We almost did away with them because of those various reasons. And then we switched over to using asphalt rubber with it. Gave us greater film thickness, meant the material could stand up longer. It also had more elasticity because of the rubber, and began to have much more durable surfaces like where Camille and I live in Scottsdale, Arizona. We saw a section go down in I think like 2000 and what year do you think that was? 2003 maybe. Very thin. It was one of the worst days of paving I've ever seen in my life. At 60-mile haul, it was winter. It looked terrible. Both of us, great engineering, we both commented to the resident engineer, this is not a good thing to do. They continued to pave. And we were sure that when they opened it to traffic on Monday, it would fall apart, okay? Lasted 14 years. They finally had to remove it because they widened the freeway. They had to do some other work. And then they put back the same type of surface. So a very, very durable surface, very good in skid resistance. Camille already showed a slide like this. Again, improvement of visibility because of the open graded nature. You saw this slide before, and this is, there were also some accident statistics that were quoted by Texas that showed that because of this, they could reduce accidents and fatalities. And then we also took skid readings with our, in Arizona we had a mu meter, which measures a skid number. It's not exactly a directly friction number, but the point is, as long as you're above about 45, and these are wet tests, these tests are done wet, your pavement is in good shape for skid resistance. And you can see that the, I can point this thing, you can see how the ones here with asphalt rubber maintained a very good number, mu meter number, a good skid resistance, wet. So that was a good thing. Also rutting resistance. You can see here asphalt rubber, we kept track of it for a number of years. The logic behind this is that pavements that rut also tend to crack sometime in here, 4 or 5 years. When they crack, more water gets into the base, and then you begin to get some rutting. And with the asphalt rubber, we don't get the cracks, so that process doesn't happen. Potholing is something we want to always resist, and I'm not going to say that asphalt rubber is totally resistant to this, but it certainly has stood up very well. I think the project being built in Indonesia and Jakarta is a good example of that, where they have a lot of potholing. So far it's performed beautifully. We don't really have much in the way of any potholes in Arizona. It's probably because we don't have much rain, for that matter, but it's rare that we see much potholing. But we want to avoid that. We've used this material in Arizona in hot and cold climates, as has California. They have some passes that go to Reno, Nevada, that are up in the high Sierras. They get several feet of snow every year, and they've had very good success with it in cold weather. This is the project that Angelo talked about. The first time I saw this project many, many years ago, I would have said, you know, let's just start over. Let's just, you know, tear it up, start all over, and put a new pavement out there. And so as it turned out, that's not exactly what we did. We did something a little different. This is this riding surface here. This was last year. This is open graded. This is gap graded. The shoulders were widened with a cement treated material because we wanted to widen out the road. It was kind of narrow, widen it out a bit. And then this is what the structure was that was proposed. This is what they would have done. They would have recycled, crushed stone, and the whole thing, quite a structure. This is what was done. Did some leveling. Took the existing pavement, was horrible. Did a little bit of leveling, and then the gap, and then the open graded. It's performing beautifully. Much less expensive. I think Angelo said 30%. I think George had this at 40%. I'm not exactly sure how they computed that number, but it was much, much less expensive. First time I actually saw this product being made was in Arizona, obviously. I was working for the Arizona Department of Transportation in 1970. This over here is Saguaro Asphalt and Petroleum. They no longer exist. They were one of the people that were actually inspired to get into this business. Atlas Rubber was a company providing the rubber. They were in California. These were actually buffings. It was not crumb rubber, by the way. That little conveyor, and they broke these bags, and it went up here into originally just an ordinary distributor truck, boot truck. And after they got enough of it in there, they had some guy they hired to go up here on top. And this stuff's hot. This is about 370 degrees Fahrenheit, or about 170 C. And he would take a long rod, a long steel rod, because the rubber would be like a cone there, and he would stir it by hand. He was a very brave man. And then they'd say, that's not quite right, so they put a little more in there, and they keep doing this. They thought, that's about right. I'm not sure how they knew that was about right. And then the driver would drive ahead about 100 yards, slam on the brakes, the stuff would slosh around, a little bit. This was the mixing they were doing. They didn't have, they had no auger drive or anything like that inside. And then you would back up and do the same thing. They do this 2 or 3 times. They say, that's it, it's ready. It's ready, it's now good. And then they would try, then they would try to spray it. And if everything worked perfect, it would spray. But many times it did not work perfect. And in fact, they actually burned up a boot truck in doing this. They got it, their theory was, let's really get it hot, and that'll be good. And they did, and it burned up the truck. So a lot of trial and error in the beginning, but eventually a company came along in Arizona and actually began to build a device that only was just pretty much for asphalt rubber. It was specially built, it had auger drives. The tips were different here, they were heated. Later on, this was all computerized, and they still build this equipment, by the way, in Arizona. This is what a modern piece of equipment looks like. And they're all over the world now. Modern chip spreader, chips here, and they supply about twice the normal binder to the surface of the road as normal, which means you're getting a greater film thickness, which is a good thing. So the original concept here was greater film thickness, chips. This was called a SAM, stress absorbing membrane. This was thicker. This material was about twice the normal amount that you would have for a normal chip seal. Because this is high viscosity, it doesn't run off the road, so you can get a lot of binder right on top of the pavement, and it's very extremely sticky material. It's been used also as just on light travel roads, just put right on top of the soil, just to cut down the dust, but it also, you can drive over it. I mean, these are primarily in the desert areas where we have a lot of dust. And then later we caught on to the idea that, you know, this seal coat doesn't give you any leveling, so let's put an overlay. And then later the overlay actually had rubber in it, gap graded as well. So there was kind of an evolution going on here. This is the normal mix, 5% binder, pretty typical. Dense graded. This is what's called gap graded in our state. Up to 8% asphalt rubber in there. And sometimes maybe a little more. In George's case, it was over 9%. And then this is open graded. Pretty much the same gradation California developed a long time ago. And they would put 6% binder. We're now putting 9 and 10% in there with the asphalt rubber. So it's a much more durable surface. Just to show you the difference in gradations, this is what you might normally see up here. A dense graded, you see all these different sizes of aggregate. The open graded, pretty much one size, and very little fines down here. Similar in some ways to an SMA, except SMAs have more 200s than we use. A lot more. So just an example of a cutaway. This is a typical dense graded in Arizona. Notice large rock and a lot of sand. Go to gap graded, a lot of rock, less sand, more rock to rock contact, less rutting. Open graded is all pretty much just one size aggregate, and a lot of rock contact. Cracking, we've had our share of it in Arizona. In my day, I've seen some pretty badly cracked roads in the old days. And in fact, we eventually became a scale developed to give us a general idea of where we were at. You can see it around 10 or 11. You're trying to get some fatigue, and then by the time you pass that, it's bad. It's really bad. And so we charted that over a number of years. This actually represents about 50,000 points. HMA with no rubber mixes with rubber, and you can see much less cracking over a long period of time. So, which was great evidence of just how good this material is. Raveling, like I said before, open graded typically would ravel, and you added the asphalt rubber, it would not. Just again, the example in Brazil. But cost is an interesting thing. George talked about this a little while ago, and we just did some figures here in the last few months for a class that Camille was teaching. So what I did was, this might be a typical activity that we would do to correct a problem on our roadways in Arizona. Quite a bit of material. You can see the cost per square meter. And when we look at that, these highways could ultimately have 20% fatigue cracking, even though you spent this much money. And these are with current bid prices. This is the comparable, this section replaces that one with asphalt rubber. over a long period of time, only a couple percent fatigue cracking, and yet, 50% or more or less than this section in real dollars per square meter. So notwithstanding what George said before, I still think that agencies like to save money. I may be wrong. I know when I worked at the Arizona DOT for 35 years, we liked to save money, and we thought we were doing an economical job. But he brings some good points, and I'm sure we'll discuss them more as the days go by. This is an interesting study, not done by me or George. This is done by California. This is actually a city of Rancho Cordova. They have been using asphalt rubber for a long time in California, very, very long time. These are on city streets. This is a city street situation. They use a PCI, which is a kind of an overall rating of the quality of the roadway in terms of cracking and other distresses. And this is representing many, many points. And you can see here that the conventional has this line here, and the line, when you use the rubber, is pushed out. So you're gaining about 7 more years of life. So in essence, it means they don't have to do maintenance as frequently or seal coat as frequently as they would if they just traditional HMA type work. So they are saving money in their minds, and this was a very good study, I might add. Again, just an example of some of the economics, maintenance cost, savings. There's a maintenance cost savings, and like I also say, there's also a safety component. Regrettably, in my state, we've had maintenance people killed by traffic, in other words, running off the road or running into them. I've had them involved in accidents. Construction zones and maintenance zones are always difficult and dangerous. So this is just one type of cost. This is just a materials cost. But there's also a safety issue cost as well to human life and limb. Environmentally friendly, we've heard, I think Camille did an excellent job on this. We recycle the tires, and there are many things that go with that. Tire fires. Tires are a great place to grow mosquitoes. I don't know if you want to grow mosquitoes, but if you want to grow mosquitoes, this is a great place to do it. So if you want to grow some mosquitoes in your backyard, get some tires, throw them out there, put some water in them, and they'll be happy mosquitoes. They'll be breeding like crazy. And you can also reduce noise. These are just some things that are more associated with the environment. This was a bad fire that they had in California many years ago. And it took a long time to put itself out. They can't actually put out a tire fire. It just has to burn itself out. So all of this CO2 that George loves just went up there in the upper atmosphere, and we're all going to die. And it's bad. And this went on for months and months and months. But then the oil residue that is created by this soaks into the soil, which costs millions and millions of dollars to figure out what to do with, because you don't want it to eventually go into the water table. So it's so you got a problem going this way, and you got a problem going that way, and it could have all been avoided if they had simply done what George said: just put the recycled tire rubber in the roadway. Right, George? Right? Correct. We wouldn't have this problem. Simple solution. And then, as like I say, it's a breeding ground for mosquitoes, pests, other kind of vermin. Noise, this was a big study that Arizona DOT and Caltrans, California DOT did, hired an expert in the area of noise. He was a retired General Motors. This man's job with General Motors was to make cars quieter. He would do all kinds of testing for them. And he told me that it was kind of in his line of work with General Motors, building cars and trucks and vans, whatever. They had a simple solution to fix a squeak, be squeaky parts. They'd get some rubber and they'd shove it where the squeak is. In other words, they used the rubber as a damper. It's like dampening it. So when he was asked, what do you know about tires? He said, well, I do the inside of cars, but he says, I'll give that some thought. And he invented some equipment. He actually invented the equipment, to measure this noise right next to the tire. And what happened here, we found that our open graded was the quietest. That's a section in Arizona on Interstate 10. The noisiest was some concrete. This was an interesting section. we've been building concrete for many years in Arizona, very noisy concrete. And the Federal Highway Administration came out with a big study, and they said, well, you're just not doing the right kind of tining. You follow this tining equation that was developed in Wisconsin, it'll be quieter. So we built it. That's that one right there. That was the noisiest section that we ever built. And on top of it, we built it right in front of the mayor of Mesa's house. And he was very unhappy about that. And we had scheduled an overlay section of concrete in the West Valley, about 20 miles from where he lived. And he objected, and he said, my road's the noisiest in the entire valley. He says, you should overlay my section of road. And so we did his first. Same was true of the governor. We had a section that went by her, we had a woman governor, went by her house, and she said, that one should be done right away. So we did. So we kept people happy, you know, just by overlaying the concrete. So it is not necessarily the worst thing in the world. However, it does get people's attention. Noise does get their attention of everyone. And then this was a study that Camille reported on, and I think he did a great job of it. Arizona State, I think, worked with other universities on this, and some in Europe, I think. The data came from Europe. So it pretty much showed what he said before. This is a great way to lower the amount of CO2, and also you're saving energy as well. So in conclusion, George already showed this slide before. It is cost effective, and it does have many, many benefits, which we've documented. I actually took this picture. I always like to relate what happened that day. We had a section of road out here we were examining on I-10, and we were cutting cores back over here. So somebody in our Rubber Pavement Association said, well, what would be the tires on the roadway? So I got a help from someone, and we got all these tires. We came out there. We're putting them out. Now, traffic is going by here at like 10 miles an hour, and we're laying these tires out on the roadway to take this picture. And they looked at us like we're the craziest people. And, you know, they're thinking like, what are they going to do? I mean, why would fools go out there and lay tires? And, you know, they're slowing down for that. It was a weird day, to tell you the truth. But it demonstrates how many tires are going in to a 5-centimeter overlay. You know, it's a lot of tires. It's a lot of ground-up rubber. And I think it's very illustrative of it, even though I got a lot of weird looks from the traveling public. The other things in here, we got cost-effective. We've seen all of these, for that matter. Sustainable, environmentally friendly, certainly sustainable. Obviously, you can recycle. The rubber effectively doesn't deteriorate in a sense, so it's there, and you can recycle the road, and no harm is done. I'd just like to finish with this one. George and I, and to some degree Camille, we've been involved in many of these international conferences, proceedings. These are available. We don't have the books anymore, I'm sorry to say, but every paper in all of these books, and there's over 300 papers, are available through Consul Pav's shop. They graciously did this. Consul Pav doesn't get any money out of this, actually. It goes to the Rubberized Asphalt Foundation. But they're all there, and if you're interested, there's a big library. We have another conference coming up in South Africa next year, I think in September. September, George? Or October? September. So you're all invited. Come by. You'll see some wonderful papers on this subject. And you'll see some lions. We're setting aside some lions for Camille because he wants to pet them. He wants a little petting zoo where he can pet the lions, so we're going to do that as well. If you have any questions, I would be happy to answer them. And if you don't have them right now, you can ask a little later or whatever. You have a question or you have a comment?
Can you please go back to that
Sure. How far
picture
back?
where you have the 14 centimeters versus 4.5?
Sure. That's a great picture. I like that one. That one there.
All right. Should we send George Way to the nut house next year too? Because look at the numbers. These are the numbers reported by Chief Pavement Engineer of the Arizona Department of Transportation. What does it say? $20 square meter versus $9 square meter. All right. You don't believe in this? Does it matter? You guys that are responsible for road networks, look at this and go home and sleep? Or you think, wow, why can't I get this? Which one is it? Or you don't believe in him?
Yeah, I may have to join you on the couch.
Yeah, let's
There
join
may
in
be
the
two of
couch.
us, I don't know.
Now, the next one, please.
Oh, the next one?
All right,
Oh, this
this
one
data
from- yeah, the city,
is
yeah.
nothing to do with George Way.
No.
This is completely different group, and this is from California, and this is from city streets, this is from roads in the network of the cities. Completely independent data. This would be like from a city from like Lisbon or Madrid. All right, you look at this data, what do you think? These guys were all drinking tequila when they make the data? Is it what goes in the brains? No, because this is the part that takes me to the loony boony, is that this means something. If I was in charge of a road network, I said, wow, 7 more years for less money? Are you kidding? Sorry, thank
It's
you.
okay, no, all right. Like I say, any comments? By the way, I did want to make one more comment. We hear a lot about global warming, right? It's obviously here today, right now, right here in this room is a great example of global warming already, if you understand what I mean. Thank you for your attention. Thank you.